Yeah, thank you for a nice introduction, and thank you for coming to this talk. I'm Kanghee Park from UW-Madison, and today I will give a talk on synthesizing specifications. Consider you're writing a code, then every program should be accompanied by a specification that describes important aspects of the code's behavior. Specifications have many use cases like test, verification, repair, or synthesis in iterative refinement of code. However, writing good specifications is often harder than writing the code itself. So our question is, can we automate the extraction of specifications? And that analyzing consequences of a program has many applications. Not only a single function, one may want to extract relation between methods within a module. And it is also related to sensitivity analysis for some differential privacy, or can be used to abstraction of domain that is difficult to reason about. Thus leads to our problem, the specification synthesis problem. Input to a specification synthesis problem is a program that contains function semantics and a set of variables of interest, and a language for the search space to the properties. For these inputs, we aim to synthesize specifications, which is expressible in language L, their sound, which means assertions hold after running program, and precise, which means no valid assertion in L is more precise than each of assertion. And we want the set of assertions to be complete. It means that adding any valid assertion in L does not strengthen the set of assertions. Let's see what it means in figure. See, a property language can say about equality between lists and comparison between size of lists. You don't need to parse the language, so let the language go away. The assertion that saying input and output list must be the same is expressible in L, but this is unsound, because that is not true for some valid input and output pair of the reverse function. A different property saying the input of output list is greater than or equal to the size of input list is sound, but it is, because it is true for every input and output pair of the reverse function, but still not precise. Because there exists a better property that says the length of input and output list must be the same, and which is precise. But sound and precise properties are not unique, and our goal is to find the set of properties that is complete. Actually, these two properties form a complete set of properties, which means that the intersection cannot be smaller than this. The key contribution of our work is to provide an algorithm to define specification in user-provided language that are provably sound, precise, and complete. In contrast, many approaches to find specification, like Daikon or QuickSpec, are based on dynamic techniques and sacrifice this soundness guarantee. So, how is specification synthesized? The algorithm uses three components: synthesize, check soundness, and our key component, check precision. The synthesis is example-based. Again, let's consider the properties is definable in the last L. What synthesize function does is to find the property in L that satisfies all the positive examples and reject all the negative examples. It would be nice if synthesize always return a sound property, but because it is example-based, it may give unsound property. That is why we need check soundness. Check soundness returns an example that must be true but not covered by the current property. And suppose we now have a sound property after synthesizing a property again. Then check soundness will say this is sound, but it may not be precise, so we move to check precision. Usually, checking precision of a property is harder than checking soundness. Say we want to find a property that is more precise than the current one, only using examples. But how can we convince that the new property is more precise? Well, it should satisfy all existing examples and need one more negative example that was not rejected by old property, but rejected by new property. And again, finding new properties also example-based, so we should check the soundness again. Now, the property is sound and precise, then the algorithm returns the property. Let's see a running example. First, we synthesize a candidate, and you found the sound property true, which is on for every program, and move to soundness check, and the check say the property is sound, and move to precision check. Precision check returns a new candidate saying that input list and output list must be the same, with a negative example that input list is empty and output list is 1,2. It moves back to soundness check, but it fails with new positive example with input list 1,2. Then it go back to synthesis. Now a new candidate is that the size of output list is greater than 0, which is unsound. So as soundness check, it fails again with positive example with empty list. And go back to synthesis again. Now I found some candidate that is sound. It passes the soundness check and move to precision check. Actually, this is one of the best property in L, but check precision may fail because our algorithm is example-based. Check precision finds a negative example with input list 1,2 and output list 1, and new candidate property says that the length of input and output list must be the same. It passes the soundness check and passes the precision check. So we are done. This is the best specification. But are we really done? Actually, we have a missing case. What if the synthesis fails? We will not go in detail how can we reach this situation, but say we have this set of examples. Each negative example can be rejected by some best specification, but there is no sound specification that rejects both negative examples. This can happen because positive example must hold for every property, but each negative example is specific to each property. One way to handle the conflicting negative example is to discard all the negative examples and reason the synthesis only with positive examples. This idea has been used in a tool Ireland, which targets to infer weakest library specifications. More recent approach is to use a stronger component, max synthesize, that finds a property that satisfies all the positive examples and rejects negative examples as many as possible. This approach has been introduced in a work that synthesizing abstract transformers of a function. Here, we suggest a new approach to handle negative examples efficiently without max synthesize. Say we found the sound property. Our observation is that either the property itself must be a best, or there must be a better property, the best property in blue circle. It means that there exists at least one best property that rejects current set of negative examples, so we can consider them safe and remember. That is the idea of freezing negative examples. So when we have conflict, we can only remove unfrozen examples and resume the synthesis with the sound property we have found. Okay, then let me show some result. Our paper applies this algorithm for 4 different domains introduced at the beginning. In this talk, we will introduce only first 2 applications. We evaluated those applications using a tool implemented by us, Spyro. Spyro implements 3 components using a program synthesizer sketch by considering property language as a program language syntax and asking to find a term that satisfies examples. But the problem to sketch was to give soundness guarantee only up to bounded input size. So we used an external tool, Daphne, to check that properties are actually sound. All the synthesized properties were sound, but properties from 23 among 35 problems were proven sound without manual effort. And except 2 problems, we were able to prove soundness only with simple invariants, like output of length function is non-negative. Let's see some specification mining example. The first example is to find properties of recursive sum function that returns sum of integers between 0 and x when x is greater than 0 and return 0 otherwise. The property language allows disjunction on polynomial equalities or inequalities. It successfully finds 2 cases of output but it does not say about when each case should be chosen. One more complex formula that is hard to parse, but it says only the first distance work when x is less than 0, and the second distance must be chosen when x is greater than 0. A different example is list element function that checks if a list has an element of value v, and here property language allows a bounded quantifier L, where the semantics of quantifier is provided by us. Again, it is not easy to parse, but Spire was able to identify that the output is true if and only if there exists an element of v in list L. And not only a single function, Spire could also synthesize hyperproperties by giving programs that contain multiple function calls. It found that applying push and then pop should give the same tag and integer that was used as input to the push. And next one is algebraic specification synthesis. A paper from Marion et al. Introduced a technique to synthesize program from algebraic specifications of library module. One of their claims is synthesis from algebraic specification is faster than synthesis from full implementation. So what they did in their benchmark is, say we are implementing a hash map from auto list, then synthesize one from mock implementation, and synthesize one from algebraic specifications, and compare the performance. From this benchmark, we try to extract algebraic specifications from implementation and compare them with the specifications manually provided by authors. In most examples, we could get the set of algebraic specifications containing what they have manually provided, but except for two cases. We will show here those two interesting cases. One is array list. A specification manually provided by authors is this one. Retrieving a value from an index after setting a value to that index must yield the same value. It seems correct, but a specification synthesized by Spire is this one. It says that, oh, you missed to check the index range. It shows handwritten algebraic specification is prone to error. Another example is specification of hash map. Again, the specification manually provided by authors is similar, but now it is correct because hash map doesn't need index range check. However, specification synthesized by Spire was just true. So what happened here? We manually investigated the code and found that the handling of hash collision was incorrect. So Spire also helped to find implementation error of program. Now, let me give the summary of our work. The first key point, our problem is to find a complete set of sound and precise L properties with provable guarantee. And our algorithm is example-based inductive synthesis that using three main components: synthesize, check soundness, and check precision. Here, the check precision is the second key point. The third point is how to handle conflicting negative examples. We remember safe set of negative examples and revert to such set when conflict happens. A missing but also keyword is, in this talk, we showed how to synthesize all best property, but our paper explains how to synthesize all best properties. And our future work includes guaranteeing unbounded soundness without external verifier like Daphne, and synthesizing more complex logics like separation logic or temporal logic. Thank you for listening to the talk, and I'm happy to answer any questions.
Hi, so I have one question about, two quick questions. So one is like, you didn't say how do you synthesize a candidate. So are you enumerating all the possible functions?
Oh, that's a good question, but we can use any technique of any program synthesis technique from example. But our implementation uses Sketch, and Sketch is kind of reducing a program synthesis problem to a single SMT query. And
so in a Sketch, you have to give a template. So are you giving a template there? Like?
Oh yes, we also provide some template, but
okay.
But for the property, we only provide the grammar and so
Okay, then it
yeah, just the
enumerates
grammar
all
is
the
template
possible-
from us.
correct. And okay, second question is about precision. So might be a stupid question, but why don't you just generate a lot of candidates and just take a conjunction of them? Because if they're all sound, then the conjunction is also sound. Like, isn't that precise? Like, what's the definition of preciseness exactly here? Like,
Yeah, that is also a great question, but the size of grammar we use in this experiment is sometimes is more than billion and usually is more than 10 or 100 million. So it is too big grammar to enumerate all the sound properties and even and for precision, we should compare all the sound properties. So it's square of the size of the
so in
grammar.
the definition of precise, you're also taking the size of the specification as some factor to decide whether this one is more precise than the other one.
Here, the size means it's the size of the search space. So.
Okay, maybe I'll talk to you offline then. Thanks.
And thank you very much for the talk. And I have a question about the freezing negative examples. Yes, you have mentioned that it will be quite difficult to certifying all negative examples, so you need to turn synthesis to maximum synthesis. And I'm quite wondering that if your grammar includes some and or operators, so you can just synthesize for each negative examples and just take the junction or something, get a specification more precise. So what is the difference between it and the maximum synthesis?
Actually, if we remember, so our paper explains that if we remember the set of negative examples, then removing all the unfrozen example is equivalent to max synthesize because it only removes this at most one negative example. So we're implementing max synthesize without only using synthesize. So
I see. Yeah. Thank you.
Okay, I'm going to make it really quick. So I didn't understand the completeness. So the idea of completeness is that there are no other sound properties in L beyond the ones you've already discovered, correct?
yes, that's correct.
But if the grammar is infinite, this is not an easy problem to solve. So I don't. How do you check completeness? What's the maybe only for specific logics or some encoding, something like that. So yeah, that's the question. How do you check completeness, and why do you think it can always be done?
So. So how we synthesize all the specification is that we modify check precision a little bit so that we find a negative example that the negative example can only be drawn from the conjunction of existing properties. So if such negative example cannot be found, then it means that the conjunction cannot be smaller than the current one. So that's how we check if the conjunction is complete. Okay. And actually, we need some assumption on the language that, like, sometimes the easiest condition is that the language is finite, but it is true that you need some assumption on the language to say determination.
Then it's clear. There is eventually a solution, so that's okay.
Yes.
Okay, thanks.